Hello friends, and welcome to a new tutorial in the series. Today I'll discuss briefly about the energy signal and a power signal. Today I'll specifically talk about how a given signal can be determined whether it is an energy signal or it is not an energy signal, and similarly for power signal. Now in this particular video I'll talk about the special case of signals, which are the exponential signals. And if you're targeting the competitive examinations or gate examination, then in the end of the video I'll tell you a short trick, very important trick, where solving the numerical and without actually mathematically calculating the energy or the power of a signal, you can immediately tell within a few seconds whether this given signal is an energy signal or it is not an energy signal, especially in case of the exponential signals. So let us move forward. As you know that an energy signal is the one where the energy is finite and the power of the signal is 0. So that is the condition for a signal to be an energy signal. The energy of the signal has to be finite value, and similarly for a power signal, the prerequisite or the eligibility is that the power of the signal should be finite and the energy of a power signal is always infinite. In order to determine whether a signal is energy signal or it is not an energy signal, there is a very small criteria which says that if a signal is absolutely integratable. Now what do we mean by integratable here? It means that the area under its curve, if it is finite, then it is always an energy signal. Please keep in mind throughout this video that I'll be talking about the exponential signals in particular. So exponential signals could either be a rising exponential or decaying exponential, depending on the type of exponent that has been given, which would be clear. I'll take a few examples in this video. So if we talk about the graph of a given signal, then you can easily make out at looking at the area under the curve. If that area comes out to be finite, then it is an energy signal. So in other words, if it is absolutely integratable, which means that the area under the curve is finite. If the area under the curve is infinite, then the given signal is not absolutely integratable and we cannot label it as the energy signal. So the one of the conditions is just by looking at the graph of the given exponential, and you can easily make out whether it is an energy signal or it is not an energy signal. So moving forward, now let us take this example. So here you have been given a time signal x of t, which is equal to e to the power 2t. Now here you can see that this is the power of e is positive, and of course which depicts that this is a rising exponential. So a rising exponential is something like this. Now if you closely notice this graph, then on the negative axis the graph is having a finite value, whereas on the positive axis this graph is increasing and is approaching infinity as the time here is approaching infinity. So as you go on moving towards the right on the time axis, this amplitude is increasing and increasing till infinity. So here we can easily notice that if we want to calculate the area under this graph, then it is not going to be finite in any case, because on the positive time axis the area is going to be infinite in this case. So here if you look at this graph and just notice closely about the area, it is very easily inferred that the area under the curve is infinite. Therefore by simply looking at the graph we can state that this signal exponential with a positive power is not an energy signal. So that is one way of determining without having to calculate the value of the energy by applying mathematical formula. So if the given signal is simple enough that you can very easily depict it graphically, and by noting the area under the curve, if it is infinite, then it is not an energy signal. So it is as simple as that. Now let us move forward and discuss one more example. Now here in this case, what I have done is I have again taken a positive exponential, as you can see here. So e to the power at, a can have any finite value, and now this has been multiplied by a unit step signal, which is u of t. And also please notice that the value of a is positive, so it is mentioned that a is greater than 0. It is mentioned that a is greater than 0, which restricts that this exponential is going to be a rising exponential all the time. And whenever a given time signal is multiplied u of t, it simply limits its existence on the positive time axis, because u of t does not exist on the negative time axis, which simply means that on the negative time axis, because u of t is having a value equal to 0, so all the time this exponential is being multiplied by 0, and hence 0 or no signal is obtained on the left hand side of the axis, whereas u of t is 1 on the right hand side or the positive time axis. So the existence of this exponential signal, which earlier in this case was existing both on the negative and on the positive time axis, by simply multiplying this signal with a unit step signal, the signal would now start existing only on the positive time axis. So even if the signal is existing on the positive time axis, we can easily make out that this signal is increasing to infinity with the time approaching infinity, which clearly states that here also the area under the curve is going to be infinite, which clearly states that as the area under the curve is going to be infinite, so the energy is also going to be infinite. And when the energy of any signal is infinite, then it is not the condition of an energy signal, which is that the energy has to be finite. So we can easily state that this exponential, even when it is multiplied by a unit step signal, is neither an energy signal and nor is it a power signal. All right. Now let's move forward and discuss some more examples, exponential only. Now here please notice that the same exponential signal where e to the power at, and this is a rising exponential where a is greater than 0. Now what I have done is I have multiplied this signal with u of minus t, that means the folded version of unit step signal. Now you know that a unit step signal is like this. It is 0 for t less than 0, and at t equal to 0 it becomes 1, and then it remains 1 for all the values of t greater than 0. So you know that u of t is 0 for all the values of t which are less than 0, and it is equal to 1 for all the values of t which are greater than and equal to 0. So when I fold this unit step signal, now if this is u of t, and you know that u of minus t is the folded version. Folded version means the signal which is at t greater than 0 will start existing at t less than 0. So you simply have to fold, or the mirror image is to be taken considering the y-axis to be the mirror. So now this would remain 0 for all the values of t greater than 0, and at t equal to 0 it will be 1, and now it will remain 1 for all the values of t less than 0. So this becomes the graph for u of minus t. Now what I have done in this particular example is I have now multiplied this exponential signal with this graph. Now when this is multiplied with this graph, then this positive part would now become 0 here. So this positive part of the signal, which was having an area approaching infinity, would now become 0 because this is getting multiplied by 0. And similarly, only this portion of the graph would now exist because this is getting multiplied by 1. So the resultant curve would look like this. Now here you can see that this is the finite value, and now this finite value on the left hand side or on the negative time axis is diminishing or reducing to let us say 0, maybe approaching 0 at time tending to infinity. So in any case, this is not approaching infinity, and we can very easily state that the area under this curve is finite and it is not infinite. So when I say that the area under this curve is finite, then it is very easily stated that because the area under the curve is finite, hence I can say that this signal is an energy signal. So I hope you're finding it easy that just by looking at the graph and the area which is depicting, we can easily label it as the energy signal or not an energy signal. Okay, now you can also calculate it mathematically, because the energy of any time signal is given by the integration of that signal, integration of the square of the modulus of that signal. Modulus means we are only taking the positive, the magnitude of the signal, and the square of it integrated over the entire range minus infinity to infinity gives me the energy of the signal. Now if you put the value of x of t here, which I have taken as e to the power at into u of minus t square. Now u of minus t, as you have just seen in the previous video here, u of minus t was existing only for the negative values of time t. So this limit of integration here will change, and from minus infinity to 0, u of minus t would be equal to 1, and from 0 to infinity it will be equal to 0. So you can very easily reduce this as e to the power 2at minus infinity to 0, and this would become the integration of e to the power 2at, which is 1 upon 2a minus infinity to 0, and you substitute the value of e to the power 0 is 1, e to the power minus infinity 0, which gives us the expression to be equal to 1 upon 2a. Now this value 1 upon 2a is very, very, very important. Why? Because any exponential signal, if integrated, will give you the value of 1 upon 2a. I'll discuss it in detail in the coming few slides. All right. So next, so as we have arrived at an expression of energy which is equal to 1 upon 2a. So exponential signal, which is e to the power at, and if it is having a finite area, will always have the energy equal to 1 upon 2a. Please remember that an exponential signal which is of the form e to the power at, a here can either be positive or negative, and if it is having a finite area, which you can always determine with the help of its graph, as we have just seen that when it is multiplied by u of t, it does not have a finite area, which clearly indicates that it is not an energy signal. And when the same signal is multiplied by u of minus t, then the area comes out to be finite, and hence it is an energy signal. Then the energy is always going to be 1 upon 2a, where a is the power of exponential. So this would greatly help you in the objective type multiple choice questions, where you will be asked to select or take the correct option as the E. So you don't have to be getting into all the mathematical calculations here, but you can always say that if the area is finite, then the energy is going to be 1 upon 2a. Next, now here in the next slide, I've taken exponential signal, but all the permutations and combinations possible for an exponential signal. So here you can see that here I have taken this exponential with positive power and multiplied by u of t, again negative power multiplied by u of t, positive power multiplied by u of minus t, and negative power multiplied by u of minus t. So these are the possible combinations of an exponential signal when multiplied by a unit step signal. Now you can very easily draw the graph. You know that for the first, now I'll talk about all the 4 possibilities parallelly. So for e to the power 2t, this is going to be a rising exponential, this is going to be a decaying exponential, then rising exponential and decaying exponential. And this, when multiplied by u of t, will be reduced into only the positive time axis part will be obtained, and the negative time axis would be reduced to 0. And similarly, whatever the graph is for the decaying exponential, when it is multiplied by u of t, we will only be left with the positive time axis part, and here the rising exponential when multiplied by u of minus t will only be left with the negative time axis part, and here also will only be left with the negative time axis part. So the graphs would look like this. Yes, so if this is a graph, just see, don't just see this portion where this is the rising exponential because the power is positive, because the power is negative, so this is decaying exponential, again rising, again decaying. Now the shaded portion which I have drawn here would be left when the respective signals are getting multiplied by u of t or u of minus t. So simply by looking at the area under the curve, you can very easily now tell within 1 or 2 seconds that this is an energy signal or this is not an energy signal. Here, because the area is approaching infinity, so this is of course not an energy signal. And see, so here the area is finite, so this is an energy signal. Here also the area is finite, so this can be labeled as energy signal. And here also the area is infinite because this will be going up and up till infinity, so this is not an energy signal. So this is one way of determining an exponent for an exponential signal, whether it is going to be an energy signal or not an energy signal. So here what we have learned is that you can never generalize that whether an exponential signal is always going to be an energy signal or it is always not going to be an energy signal. So it all depends what part of the wholesome signal is left when it is multiplied with other time signal. So in this case, unit step signal. So this is a crux where you can easily know it with the help of a graph. And now comes the time for the trick. The trick is very simple, so it will reduce the time required for solving the questions from seconds to a fraction of a second. And the trick is that whenever you have been given an exponential signal which is being multiplied by unit step signal, then you have to apply this trick. If the sign of, now what you have to see, you need to look at the sign of the power of e and the sign of t in u of t. If both the signs are same, then the signal is neither energy nor power. Whereas if the signs are opposite, one is positive, the other is negative, or one is negative, other is positive, then it is an energy signal. So here you can see that in the first case here, the first case, power of E is positive and T is also positive. So both the signs are same and signal is not an energy signal. Here the power of E is negative, but u of t, t is positive, so both the signs are opposite, so it is an energy signal. Similarly here the signs are opposite, so it is an energy signal, whereas here again the signs are same. This is also negative and t is also negative, so it is not an energy signal. And whenever you conclude that the given signal is an energy signal, then as I've already told you that the energy is always equal to 1 upon 2a. So whatever the value of a is, so here when this is an energy signal, so its energy is going to be 1 upon 2a. So a is 2, so the energy is going to be 1 upon 4. And similarly for this, where the area is finite and it is an energy signal, energy is equal to 1 upon 2a. So a in this case is 3, so the energy is equal to 1 upon 6. So as simple as that. So I hope this quick tutorial was of help in determining whether the given exponential signal is an energy signal or is not an energy signal. So I'll see you soon in more such videos. Till then, keep watching, keep visiting the channel. Have a good day, have a good life. Bye bye.